the Northwest Fisheries Science Center and the Alaska Fisheries Science Center, and it was started as a tribute to Don Bevan. Don's academic career spanned 50 years, almost 50 years, and he was during that time a director of this very school, a director of the larger College of Fisheries at the time, and his work focused on the intersection between science and economics and politics, and he was involved in the authorization, the enactment and reauthorization of the Magnuson Act, which governs our fisheries in the US. He tirelessly worked to ensure that fishery managers, industry, and scientists spoke with a unified voice in making policy work for America's fisheries. In this series, we seek to continue and extend his legacy by focusing on current issues related to our fisheries. We try to look at as many viewpoints as possible, and this year's seminar series is focused on a particular issue of concern to many, which is ocean acidification. This is a process where extra human-caused carbon dioxide released into the atmosphere ends up in the oceans, making them more acidic and potentially affecting both agriculture and fisheries. Sometimes this is called the evil twin of global warming, the other effect of carbon dioxide. I can think of nobody better to introduce this series than Dick Feely, and I'm going to hand over to Jan Newton to give a proper introduction to him. Thank you very much.
Well, it's my extreme pleasure and honor to introduce Dick Feely, and I just want to say that the Pacific Northwest is really lucky to have one of the premier experts on ocean acidification in our yard. I'm not going to say our backyard, because he is at NOAA PMEL, but he's also an affiliate professor here in the School of Oceanography, so that's our own yard here. And I could easily introduce Dick by just saying that many of us know him and work with him, and so here he is. But in fairness, I really want to take a moment to note some of his accomplishments, because I think they are quite impressive. And first off, and this one is a little bit tongue-in-cheek, but this esteemed oceanographer started his undergraduate training in the Midwest, in Minnesota, and then realized he wanted to study the oceans and got his master's and PhD at Texas A&M in chemical oceanography, and then made his way out here to the Pacific Northwest. Dick's numerous contributions to the field of chemical oceanography are dominated, I think, by his recent focus on carbon dioxide and the issue of ocean acidification. He's a really good leader, and that's been shown by his leadership landing him in spots like the co-chair of the Clybar CO2 repeat hydrography program, and also on the steering committee of the U.S. Carbon and Biochemistry program. In 2006, Dick was awarded the United States Department of Commerce Gold Award for his research on ocean acidification. In 2007, he was elected a fellow of the American Geophysical Union, and most recently in November 2010, he was awarded the Heinz Award for his pioneering research in ocean acidification. So all of those awards and accolades make you think that Dick, has his head in the clouds and is the typical academic. But what I really admire about Dick is his sense that it isn't enough for a scientist just to publish to scientists, which he has 200 peer-reviewed publications. But he has also been asked to brief the United States Congress 4 times. I know he's spoken to leaders here in the Washington state government. He's sought after by diverse audiences, such as leaders in the shellfish aquaculture industry, public science venues like the Pacific Science Center and the Seattle Aquarium, as well as filmmakers, and you're going to hear from one of those later in this series. The film Sea Change even landed him on stage at the Seattle Film Festival, and I got to be on a panel with him, so I guess I owe him thanks for my stage career as well. Very brief. Anyway, it's really been my honor to work with Dick and his group. I see Simone here, and I bet Chris is here somewhere in the audience, over the last several years to look at ocean acidification in Puget Sound, but also to get to know him as a person. And I consider him to be one of those great people who are really excellent at being a scientist, a mentor, a citizen, and a friend. And at lunch I learned that he once said there isn't a question that he's been asked about ocean acidification that he hasn't heard before. So there's your challenge. So there's no person, as Trevor said, to kick off this seminar series better than Dick Feely.
Thank you, Jen. It's a wonderful introduction, and thank you, Trevor, for arranging all this. This is an outstanding group of speakers for this special seminar series on ocean acidification. I'm proud to have worked with most of these people. They're close friends of mine. And you're in for a great opportunity to talk to the best of the best on this field. And it's really a good treat for me to be able to take off. I'm also thankful to the Bevan family to be supporting this. My job, I think, here today is to give you just a brief overview of what ocean acidification is all about. So I'll try and touch upon all the various aspects of ocean acidification. I would like to then answer some questions at the end and then follow that up with one or two more slides at the very end. So give you just a kind of a broad perspective on this. So I'll try and address some of the things that, well, I hope will be brought up by the following speakers to give you something to think about for each of this teaching. So let's get started. So what I'd like to talk about, first of all, is what is ocean acidification, the science of it, how it works, the results of what we understand from observations and surveys. I'll talk a little bit about what the deniers are saying and what the responses are. And what are the potential biological impacts. I think if there wasn't biological impacts, we all wouldn't be here. So those are particular consideration. And what we as a nation are doing about that. So the first slide I want to show a little movie slide I'll show here. This is the global network for atmospheric measurement for carbon dioxide. Our sister laboratory, the Global Monitoring Division of NOAA, maintains this atmospheric network of 60 stations throughout the world. And this is the record of CO2. And I got this started a few years ago. And this is the South Pole here, and here's the North Pole here. I just wanted to show you what the trends are over just a few short years of observations. To show you very, very clearly that mankind has had a significant impact on atmospheric CO2. So here is the, that's my fault. Not a very auspicious start, is it? I put my hand down and work. So here's the breathing of the Earth, the uptake of carbon dioxide in the summertime, which is very prominent in the northern hemisphere, and the release due to predominance of respiration in the wintertime, which gives you high CO2. The northern hemisphere is dominated by CO2 sources in the industrial countries, and the southern hemisphere is mostly dominated by oceans. But you can see from this very simple slide that the background of CO2 is increasing all the time. It increases at the rate on average about 1.5 parts per million CO2 in the atmosphere because of the release of fossil fuel CO2 from the burning of coal, and oil, and natural gas. Over the last decade or so, it's increased to almost 2.0 because we're increasing the rate of CO2 released in the atmosphere. On average, that's been about 3.4% increase to the anthropogenic release of CO2 into the atmosphere. And we released about 9 billion metric tons of carbon into the atmosphere. That's we refer to it as 9 petagrams of carbon. 9 plus all these zeros after that. It's hard to count all the zeros, but it turns out to be times 10 to the 15. And if we look at it from this perspective, this is Simone Allen put this slide together. A railroad car holds about 80 U.S. tons of coal. And so this railroad car for every year would go around the Earth about 56 times. That's how much coal carbon we are burning and releasing into the atmosphere each year. Now what that does is it increases the CO2 concentration in the atmosphere. This is the Mauna Loa station, the longest record of CO2 in the atmosphere right here. This Dave Keeling started this in 1957 and continued it through his death in 2005 and is now maintained by the NOAA laboratory in Boulder. And what I showed underneath that was the Hawaiian Ocean Time Series station of CO2 measurements in the surface ocean. This is the peak CO2 measurements here. And you can see that the CO2 in the oceans, the peak CO2 in the oceans, increases at approximately the same rate as the atmosphere. The oceans are taking up that carbon dioxide at about the same rate. You can see here the rate is approximately equal. And here's the corresponding pH trend here for the same measurements. These are very interesting measurements. They're taken 2 different ways. Very good results. And we see a trend then of a decreasing pH of about 0.02 pH units per decade. So we are seeing from measurements alone the effect of the human's impact on the atmosphere from the burning of fossil CO2. We've done this many places throughout the world oceans, in the Atlantic, off of Bermuda, and off of the Canary Islands, and we get pretty much the same effects. And from cruises we know throughout the world that this is occurring. So when you go through the IPCC process, determine what the overall impact of anthropogenic CO2 emissions are. Generally speaking, we get about 1.5 petagrams of carbon per year from the burning of fossil fuels, and then an additional 7.5 from burning fossil fuels, 1.5 from deforestation. And that distributes itself into about an increase of 4.2 petagrams of carbon per year into the atmosphere. So 46% of it remains in the atmosphere. About 2.6 goes back into the land. This is terrestrial regrowth, mostly in the temperate zones of the Earth. And then about 2.3 petagrams of carbon goes into the ocean. Now, up until about a decade ago, we thought this uptake of carbon dioxide in the ocean was a good thing. Because if you think about that uptake of carbon dioxide has reduced the atmospheric concentration by about 75 parts per million or so, and therefore it has reduced global warming by as much as a half a degree C. So we all thought, oh, that's great, let's get it all into the oceans. And when you look at the numbers, you see we are building up carbon dioxide in the ocean now. About 234 petagrams of carbon has gone into the atmosphere over the last 200 years. 127 petagrams of carbon in the ocean, about 25%, and about 147% petagrams of carbon, 29% in the terrestrial biosphere. Most of this in the terrestrial biosphere in the first 150 years or so, and now we have a significant increase going back into the terrestrial biosphere as of late. And the oceans are slowing down their rate of increase relative to the atmospheric increase. It used to be about 31% about 30 years ago, and now it's down to about 25%. So they're not keeping up with the atmosphere overall in the amount that's being taken up. So here's your first myth about the issue about ocean acidification. I think of it climate denier statements. The oceans will never become acidic. So calling this is called ocean acidification, is just being alarmist. So what's the truth about that? Well, the truth is that acidification is just the term for the process. As you add CO2 to the water, you are clearly decreasing the pH. And therefore, that process is moving in the direction towards acidic conditions. oceans are at a pH of about 8.1. Their acidification will move it towards neutrality. And this process is called acidification. They are basic now, but they're moving more in a condition of acidity. Same thing if you were in Minnesota, where I grew up, and it was 40 below zero, you didn't want to go outside. When it got to be 10 below zero, you thought, this is a warning, this is a proof. It's pretty darn cold at 10 below zero, but we call that warning. This is the same analogy here. We're moving in the direction. Made for the process. That's the important point to remember. Now, one of the clear things that we know from the geological record is that the rate of change is much faster than anything we've seen in the geological past. And we can see here that this CO2 chemistry changes over the last century is in the neighborhood of 100 times faster than anything we have seen in the recent geological history, going back at least 50 years or so. And this is the same thing true for the temperature. We are increasing the temperature much faster than in the geological past. So what is ocean acidification? Well, CO2 is an acidic gas. It reacts with water, seawater, to form carbonic acid. That carbonic acid immediately dissociates to form a hydrogen ion. That's what gives us our acidity. That hydrogen ion then will react with a carbonate ion to form bicarbonate. Now, the carbonate ion is one of the principal structures of a calcium carbonate shell or skeleton. So the destruction of the carbonate ion means that it's more difficult to form skulls and skeletons. So what we know from the geological record in the recent data sets is that the pH of CO2 on the surface seawater on average was about 8.2. It has decreased about 0.1 units from the pre-industrial to the present. And the carbonate ion concentration has decreased 60%. That pH 0.1 unit decrease has increased the acidity of the oceans, the hydrogen ion concentration, by 30% since the pre-industrial. If we take the IPCC business as usual scenario, the best guess scenario, we would see another 0.2 to 0.3 pH decrease near the end of the century. This would be an atmospheric CO2 level of about 800 parts per million in the atmosphere, and a corresponding carbonate ion decrease of about 50% or so. That decrease in pH of 0.2 to 0.3, something like that, would be 100 to 150% increase in the hydrogen ion concentration by the end of the century. I think you all would agree that's a significant change. Now, for the organisms that produce a calcium carbonate shell or skeleton, what they are concerned about is what we call, as geochemists, the saturation state. When the saturation state is greater than 1, they can produce their shell or skeleton. When it's less than 1, that skeleton will begin to dissolve. Those waters where it begins to dissolve, I call corrosive. And that's the point we are making. They begin to dissolve away, so they're corrosive. So that saturation state is the calcium concentration, which for the most part is constant over short geological time periods, times the carbonate ion concentration, which we said was just decreasing because of the addition of the CO2, divided by this apparent solubility product. The apparent solubility product increases with decreasing temperature and increasing pressure, which means in the cold waters deep in the ocean, this number gets larger. So this saturation state gets lower, and at some point it gets less than 1, and the shells will dissolve. If you look at distributions of the shells in the water column, you can see the evidence of dissolution when it gets below this equilibrium point. And we do that with sediment. And in the warm tropical waters, for these calcite species, this saturation state is about 4 to 6 or so, 2 in the cold, high latitude. For aragonite species and for calcitic species, it's about 5 to 7. So there are different morphologies of the mineralogies, and different mineral phases affects that saturation state. And this has all been worked out by the geochemists with tremendous precision and accuracy. We know it quite well. So the most common minerals are aragonite, which is the most soluble. This is things like coral reefs or pteropods. And calcitic forms, some clams and oysters are calcitic, which are the less soluble. So we as humans have to think about what's going to happen to CO2 emissions. Because as we release CO2, we have to decide what level of CO2 we are going to stabilize in the atmosphere. And what CO2 emissions that we will allow us to stabilize that. The important part of this slide is whatever stabilization scenario we predict for the future growth of CO2 will end up with an atmospheric concentration and a pH change. And that pH change will be with us for a significant period of time, hundreds of years or so. So the changes that we make now by releasing CO2 in the atmosphere will have significant implications for what that pH change will be over the next 200, 300, 400 years, or even 1,000 years or more. So what we have done in part of the U.S. and the international community is in the decade of 1990s is to develop a first global CO2 survey. The first one was actually done in the 70s by the Geosix group, and then this was the second one that was occurred in the 1990s. The first one had 5,000 samples. This one we had 72,000 samples, 8 countries, 15 laboratories working together. We took 10 years to collect this data. We took another 5 years to collate and make all the corrections to data. So we had a very highly precise and accurate data set throughout this world. Our laboratory, along with our sister laboratory and groups of Princeton, collated all this data and got a tremendous understanding of the distribution of antigenic CO2. We did this by going on ships and collecting water samples from surface to bottom. These rosette packages had 32 bottles on them. We now have CO2 sensors that are on moorings, and we're working towards getting them on floats and gliders. So that's where we are. We collect the samples on board ship. We do all analyses aboard the ship. Many of my group members are here, and they've done all these analyses. And it's pretty impressive that you can do a whole 32 rosette sample, collect all the samples, analyze the samples, and be ready for your next 6 hours later. And what we end up with is a distribution of man-made CO2 in the oceans, the VIC concentrations of Atlantic CO2. This is the Atlantic here. You can see it penetrates all the way to the bottom of the Atlantic. And here's the Pacific and the Indian Ocean. And you see most of the anthropogenic CO2 is still in the upper part of the ocean. In fact, almost all of it is still in the upper 1,500 years. This is a slow circulation in the ocean, which takes 1,000 years or so to go from the North Atlantic where the water sinks to the North Pacific where it comes back. And so this slow circulation process means that most of the anthropogenic CO2 is still in the upper part of the ocean where our organisms live and are impacted by that. And what we see is about 60 micromoles per kilogram in surface waters penetrating down to 1,500 meters to background levels of about 5 micromoles. We know this very, very well from our measurements. We are now repeating those surveys to see what the changes that are taking place over the last decade. Now what we have done is we've calculated where this corrosive, the saturation state equals 1, where this corrosive water exists in the oceans, and it's quite different. In the newly formed North Atlantic waters, it's still very deep. The saturation state is about 2,500 meters for aragonite, 3,500 meters for calcite. There are some places in the eastern Atlantic where it's shallow. But most of the corrosive water is very, very shallow in the Arctic Ocean in particular, along the coast of Alaska, all along our coast, where in Alaska it's as shallow as 100 meters. Along our coast it's as shallow as about 200 meters, right at the shelf rate. You can imagine if there's any way to get that water on the shelf and impact those organisms that live on the shelf, we've got a problem. And you can see it extends all the way down to South America and also in the Indian Ocean. This is following the pattern of the global circulation of the oceans, where the water starts and sinks in the Atlantic and moves from the Indian to the Pacific, so that the oldest water in the deep water in the Pacific, it has about 10% more CO2 than in the Atlantic because it's so old and has been accumulating all this respiration projects of contained organisms. And so the corrosive waters are very shallow. Now you're adding to that the anthropogenic CO2 from above, and causing a shoaling of those horizons towards the surface. And in fact, what we have found is that in the Pacific, that is a shoaling of about 1 to 2 meters per year. In the Pacific and Atlantic, it's about 4 to 5 meters per year because it's country. So we worked with the modelers, and some of the modelers have now developed projections of when this corrosive water, saturation state less than 1, will actually reach the surface. And so because the waters are coldest in high latitudes and more CO2 goes into the water at high latitudes, we expect to see that in the Arctic Ocean, if the model suggests that in the next decade, around 2016 or so, we begin to see the surface waters of the Arctic Ocean become corrosive, and that would then penetrate downward into the North Pacific Ocean. And the same thing is true in the Antarctic regions. We can see about 2050 changes over where the surface to bottom, the water will become corrosive, and we retreat towards the tropics. And even in the tropical regions, we would see impacts where the saturation state would be dropping. That's what the model suggests. The reality is that we are seeing coastal water right now in the Arctic Ocean at the beginning of 2008, faster than the models projected, because we didn't account for the melting of ice in the models accurately enough. And so we are seeing this process occur faster in observations than we see in models. Another denier question that comes up all the time is, okay, you have such a big natural variability, when are you going to see that the changes that take place due to anthropogenic CO2 is going to extend beyond that natural variability? And my good friend and one of the speakers, Scott Doty, and his colleague Sarah Cooley wrote a paper about this, showing that, looking at the variability, what years does it begin to get so low that it no longer exceeds is within the envelope of the natural variability. And they did this by mapping it out by year, but showing a couple of examples. And then at Station Papa, which is in the Northeast Pacific right here, we can see that we get lower than the natural variability by about 2050 or so. And at the Aloha Station, which is much lower variability, we can see an impact as early as 2020 or so. So we can see that we are rapidly progressing to the region where we'll be in a new state relative to the natural variability that we see. And this is a map here of the dates when these would actually exceed their variability. And for the most part, you see it browns, which would be in 2020. Not too far from that, just a few short years. So we are really changing the state of the oceans quickly. This next movie will show the changing state from the pre-industrial starting in the 1880s of the saturation state of the surface waters. Very good situation, high saturation state, 3 to 5 are the blues. Very difficult situation for calcification are the yellows. And when you get into the bright dark reds, that means we're in corrosive waters. So we start out in 1880, and you begin to see very dramatic impacts beginning in the Arctic Ocean and in the Southern Ocean because of the input into the cold, high latitude regions. But you see dramatic changes also in the tropical region. By the time we get out to the end of the century, you see the entire oceans have changed. And this is just a business as usual scenario. By the way, we're now releasing CO2 in much higher rates than the business as usual scenario that's projected here. Whether we continue that rate is unknown. Here are some recent estimates based again on the Doty's model on the pH changes that would represent, and we can see in pHs on the range between 8.1 and 8.2 in 1875, and by 2100 the pH ranges are from about 7.6 to about 7.8. Major pH changes correspond to changes in CO2. In coastal regions, I mentioned that these corrosive waters are sitting at the shelf rate. So what happens when we have upwelling events? On our west coast of the United States, upwelling is a common feature when the winds shift from being from the south in the winter time to being from the northwest in the summertime. That causes the surface waters to move offshore and the cold waters, nutrient-rich waters, move onshore, and therefore you have a natural upwelling. This is what maintains our beautiful productivity and high fisheries on our west coast, but it is also bringing these corrosive waters onto our continental shelf region. And in 2007, we worked together with our colleagues from Canada and Mexico and a number of colleagues along the Pacific Northwest here to study this. And we did 13 lines from Queen Charlotte Sound in Canada to Ensenada in Mexico to study what was occurring. We were looking to see for evidence whether there was any kind of corrosive waters on our shelf. And we since then have been developing moorings out to see. This is work that we do with Jan Newton and our colleagues here at the University of Washington Physics Laboratory, as well as our colleagues along the coast, beginning to study this process. And the process is that the corrosive waters would move up along the bottom, reach the surface near the beach, and then go out at the surface. And this is what it looks like when we make those measurements. This is off of Northern California. Here is a temperature map with the density map on here. You can see that the density of 26.2 gets upwelled all the way to the surface, 26.4 all the way to the surface, but near the coast, even as much as 26.6. It doesn't quite get there. You can see the corrosive waters on that 26.2 just simply being upwelled to the surface. So all this water here is corrosive. And we see that the pH of these waters are as low as 7.6. So what the models predicted would be on our shelf region in 2100 or later are on our shelf region right now because of the acidification process. And about 30 micromoles of this corrosive waters is due to anthropogenic CO2. It's enough to make the waters corrosive in this region. So we are seeing an intensification of this process because of the natural process of upwelling and respiration combining with the anthropogenic CO2, concentrating on the corrosive effects on our coast. Now here's a model output I wanted to show you. This will start basically in January. This is Nikki Gruber's model for the coast from Washington to Southern California. Here's temperature. Here is pH. The upwelled corrosive waters are in blue, starting in January, and we'll step through the year to show you what the impact will be. So we go through the year, and you can see the beginnings of this in March and April, developing through the summer, staying through the whole region through the summer, upwells to the beach, and then moves out, and it gets consumed by production in the interior of the oceans. And this will then be repeated year after year. So you can see the upwelling process brings it all the way to the beach and then moves it out. So if that process of upwelling occurs on our coast, we ought to ask ourselves, what's happening in Puget Sound? Because much of our water that we get in the deep water of Puget Sound comes from upwelling process on the coast. Jan Newton was worried about this and invited us to participate with her on the prison cruises, and we did so, and we also were invited to work with her on the moorings that they have out in Puget Sound, and we're putting CO2 and pH moorings. That's Chris Sabine's work with Adrian Sutton. And Simone Allen went out on the cruise with Jan on these to begin to see what the impacts would be. And our thought was that the upwelling process would bring in corrosive waters into Puget Sound and might see these impacts. And so what we have here is a data set from the coast all the way to Hood Canal in August of 2008. Here's the salinity on top, the oxygen distributions, the pH, and the aragonite saturation. And what we found is that during the upwelling events, the water spills over through Edmonton Inlet and pours into the main basin of Puget Sound as well as Hood Canal, but it combines with waters that are already acidic because of hypoxic conditions. So that in Puget, Canal, and Puget Sound, we actually have lower pH values than we see anything on the coast. This means we have to begin to think about the juxtaposition and the cumulative effects of acidification and hypoxia working together to lower the pH in our coastal systems. This had not been talked about anywhere in the literature, except for when we published this recently in the National Coastal Science. So we now have to think about combined impacts in our coastal regions and their impacts on acidification. Our estimates show that acidification accounts for anywhere from 24% to maybe 49% of this pH lowering in the lower council. But projections would say by the end of the century, acidification will be the dominant factor. Again, in our estuaries, we need to think about this problem as well. It's true for many estuaries. Now I'm going to shift gears a bit. Now I want to talk about the biological impact. And I'm going to show you a whirlwind of impacts and a lot of different kinds of impacts, so stay with me. It's just to give you a broad view of the kind of impacts you're going to hear about in the coming lectures. When we do acidification process studies, we do them under laboratory setting, as done here. Friday Harbor is going to be one of the major facilities for doing that. Murray here is going to be one of the leaders of that, working on how we set up experiments in which we actually add CO2 into a aquarium type situation and seeing what changes occur in the species. You can do that at the mesocosm level here. This is Biosphere 2. Have a whole mesocosm study, a number of different species. You can do that in the open ocean, studies between those. And you can have whole ocean studies where you put a tent over as a system to change the study. So a variety of different approaches are being considered. Mesocosm approaches are taking hold. Friday Harbor, I hope, will be one of the leading facilities for that. And when you do those kinds of experiments, you can see what the impacts, and this is the Biosphere 2 experiments that Chris Langdon led in the early 2000s. And what he showed is that for coral species in Biosphere 2, there was a very clear relationship between decreasing calcification, how fast they made their skeletons, and saturation state. Different for different species, but all tending in the same direction. This has been done over and over again. You see that. So here's an example of how ocean acidification affects the calcification process. It's kind of important because corals have to grow fast enough to continue to grow in order to be in the light and competing with sea level rise. So if they slow down, they've got a problem. Here's some field studies that have been done by Eve and colleagues to show what we know from just studying how fast coral species continue to calcify. And this was done in the Great Barrier Reef with 320 priority samples from 69 sites in the Great Barrier Reef. Now what they found is a significant increase in calcification rate and extension of the pearls beginning in about 1990 or so. And overall, it's been a decrease of about 14% over that time frame. Roughly about 1% year decrease. Now, we don't know exactly from these studies whether this is due to the temperature changes, due to global warming, or is it due to the CO2 changes? We've got to do those kinds of studies. But this has been repeated elsewhere in Panama and other regions, and they get the same kinds of rates taking place. It's certainly a concern for coral species. Here's some work that Justin Reese did in a laboratory setting at Woods Hole. He was there as a postdoc, looking at a number of different calcifying species. And from his studies, he's shown that the majority of species show a decrease in the calcification rate, but not all. Some actually increase. Some increase and then decrease. So you have to look at what the impacts are species by species. And the thing is that in some cases, we think what's going on is the organism is actually spending energy to maintain calcification at the expense of other processes in their life. Crassostreo do that. They maintain calcification in high CO2 world at the expense of their muscle mass. They use energy to save the calcification process. What kind of interactive processes are occurring that we don't know much? If we go to the phytoplankton and zooplankton and the first levels of the system, you might see there are about 200 species of calcite, mostly calcitic, 30 species of protozoans, Foraminifera, and 32 species of pteropods. What we see so far is some very clear evidence that at higher CO2 rates, calcification decreases for calcite, but not all species of calcite. Still, it's confusing. Some species seem to do better. We need to know why and what's going on. Some of the species show the malformation of the shells, significant decreases. The Foraminifera shows the best evidence so far that there's a decreasing shell weight, and with the increased CO2 levels, that's very consistent. The Foraminifera have been shown in sediment traps and sediments. Look at the most recent work on sediment trap samples. Those forams are lighter, less shell weight, thinner, and smaller than what we see in sediments just 100 years ago. The work that Vicki Favre has shown is that the living pteropods, that we can see that dissolution occurs within 24 hours. Significant dissolution of shells are placed in high CO2 waters while they're still alive. And when we look at mussels and oysters, we see a decrease in calcification rate. Mussels, which are more aragonitic, see more of an impact than oysters. Now, the work on the East Coast has shown with clams, is that Mark Green has shown that juvenile species tend to be more sensitive than the adults, and we find massive dissolution within 24 hours. And that dissolution can cause mortality within 2 weeks. You can see here in the high-resolution photographs the dissolution process of these juvenile clams. We look at sea urchins, and this is Gretchen Hoffman's work from the University of California, Santa Barbara. We can see that the sea urchin limbs, which are calcium carbonate limbs, have become shorter, and she's done some of the first work with genomics to see what the impact of CO2 on the genomics of the sea urchins, which are well documented. And you see a significant change in high CO2 levels, down-regulation of those genomes for acid-base reactions, and a number of other reactions as well. And that down-regulation is a process then to determine what the gene expressions are, and at what point will they just simply turn off? That's what her group is trying to work on. She will be here later this month to talk about it in detail. Some of our old work here in the Pacific Northwest is focused on the impact in the food chain when coccolithophorids, marine plants, are eaten by the pteropods and pteropods. That's the food source for the salmon. And the work that has been done here by the Natural Marine Fisheries Service has shown that a 10% decrease in pteropod production would lead to a 20% weight loss in salmon. So this is really kind of a critical issue for us who are very concerned about our seafood industry. If you look at the scorecard of what we know so far, the basic is we don't know a lot yet. It's just a few number of species we looked at. The scorecard is a little bit old. It's not up to date. But we have looked at calcification. Most studies of calcification show a decrease with the increase in CO2. As I said, some species seem to go in, increase. Some species stay the same, and some are different. So you have to understand species by species. So far, photosynthesis, most things we've looked at show an increase or the same. Even if it's increased or the same, it means that some forms of phytoplankton will do well, and other ones won't do quite so well. Some of the recent work that just came out in PNS showed that acidification can directly impact nitrification processes, which means that the whole nitrogen cycle could be tremendously affected, which would then again affect phytoplankton production. It's a very brand new work that Dave Hutchins and group have been working on that suggests that not only is the carbon cycle affected, but perhaps the nitrogen cycle as well. And therefore, we might expect to see impacts on nitrogen fixation and impacts on reproduction as well. So, what we know so far is, in the literature, is that there are reduced calcification rates Potential for significant shifts in nutrient distributions, as I suggested, in terms of the nitrogen cycle in particular. Effects on trace metal speciation, effects on iron and copper have been studied so far. Potential for impacts on phytoplankton composition and diversity, reduced growth, production, life, plants. Again, perhaps the juvenile and larval stages that don't have the energy reserves will be more sensitive than adults. Reduced tolerance to environmental factors. Now, if you think about it, for example, coral bleaching is enhanced in a high CO2 world. That means that combination of increased CO2 and warmer temperatures will enhance coral bleaching. What kind of other examples that we have? A combination of factors having an impact. There are other things that have yet to be studied. They're just getting some initial studies on effects on sun absorption, effects on homing ability of organisms, even to avoid being eaten by predators. It seems to be impacted. Effects on improvement and settlement. We really know little about the biogeochemical changes and movement changes. This, you can see, stems to what little we know about how much we need to know about how the ecosystem responds as a whole to these kinds of changes. Uncertainties are great, and a lot of research is required. This is a very new field of research. It really began in the 1990s. Chemists knew about it for 30 or 40 years. They just got around to telling everybody else about it. And biologists really took off in the 1990s. Why do we care? Well, in the United States alone, the seafood industry is about $4 billion per year, and that represents as much as a $60 billion industry as a whole. And about 50% of that $4 billion industry is just the shellfish alone. And when you consider that shellfish provide food for about half the fish, you're talking about 3/4 of the seafood industry. And Scott Doney will be here to explain that. I want to end up with a couple of examples of what we know in the field about how this is occurring and why it's occurring, how we know it's occurring. And one of the best examples I can think of is the work of Jason Hall Spencer and colleagues, who went to an island off of Italy called Puget and studied the effects of ocean acidification in a world where CO2 levels are much higher than they are now, because the carbonates are being burned in the geological substructure of the Canal, releasing pure CO2 into the water column. And it's a very small area, and you can see the impacts. And what he have found is that all the calcium carbonate-bearing species decrease in relationship to the location of that CO2 source, but seagrasses increase. Again, what that suggests is that whole ecosystems can change. There will be winners and there will be losers. And as mankind, we have to figure out, are we concerned about who are the winners and who are the losers, and how will ecosystems respond accordingly? And what they found was that all the calcium carbonate species declined in this region, including the corals that they put in there. And there was a tipping point at a pH of about 7.8 for the species. His later work showed that in that region, where the high CO2 waters existed, there was a 30% loss of biodiversity. Now here locally, we have a problem with the hatcheries that produce oysters. This was discussed in the public literature by Craig Wells, widely impacting oysters and its ocean chemistry affecting that. And what they found is that since 2005, the larval stages of the oysters, which have a lifespan of about 15 days or 20 days before they settle to the seafloor and become oysters, these larval stages are very susceptible to changes in CO2 level. And they either die in the water column before they settle out, or they settle and die. And in the hatcheries, they were finding as much as 80% die-offs between 2005 and 2008. And this was a point where the hatcheries were going to go under. They had to get their colleagues in the seafood industry help support them to stay alive. They went to Congress and asked Mary Cantwell for help. She used a little bit of stimulus money, and they got the scientists involved with this. And I want to stop here and show you the presentation that was on Good Morning America on this topic. This is, you can tell their story. And this was on Earth Day this past year. You should be hearing the sound.
Did you know that the 70% of the Earth's surface is covered by the oceans, and those oceans absorb about 20 million metric tons of greenhouse gases that we put into the air just about every day. Now, we never really thought there was a problem before, but now we're beginning to think it might be. Mark Waggart and Sue Cudd have each dedicated 30 years of their lives to bringing oysters to our tables. Now the couples found themselves thrust into the forefront of one of the newest, most pressing environmental issues of our time. And it all began with these tiny, delicate oyster larvae.
In 2007, all of a sudden our larvae started dying.
The husband and wife team run the Whiskey Creek Oyster Hatchery in Oregon, the largest independent producer of commercial oyster larvae in the country. They produce 10 billion a year for shellfish farmers around the world to grow into the oysters that we recognize. That is until their production plummeted to zero without any warning.
At first we thought, what are we doing wrong? After 30 years of being able to produce larvae, all of a sudden we can't.
Desperately, they turned to expert oceanographers. They discovered the Pacific water piped into the hatchery from Netarts Bay outside the door was to blame. And it wasn't just them.
This is where the Pacific Ocean meets Netarts Bay. Every day, those waves refresh this bay. That water is roughly filtered, heated a little bit, and pumped directly into these 8,000-gallon tanks. Inside the tank are roughly 40 million swimming oyster larvae. If they're not swimming, that's a problem.
Scientists discovered something was making the water too acidic, preventing oyster larvae from growing shells, and without the shells, it's certain death.
So you can see this is a real life problem that we're faced with. We had the same problem at the Taylor Shellfish in Bivalve Bay. So they came to us, we began to work together with them, and with the support from Congress, we were able to take some of the stimulus money and put these same CO2 sensors in the hatchery that we have on the ships in the moorings and begin to address this issue. And what we found was, and this is the hatchery scientists showing their data, that when the winds were from the south, which means upwelling wasn't occurring in low salinity waters, there's great survival of the oysters, high saturation states. When the upwelling favorable winds were from the north, higher salinity waters, upwelled waters were occurring, and the mortality rates were extremely bad, and the saturation states were low. That's the information that we have right now. We are now working together through a Sea Grant program with the National Fisheries Service, Carolyn Friedman here at the University of Washington, to address this issue in the laboratory and hoping to really get at the bottom of this kind of a problem, this kind of cooperative work with the University of Washington, the shellfish growers, and the federal agencies is the way we should properly move forward on these kinds of issues. If we look at what we understand so far, this is kind of a summary diagram put together by Carol Turley and colleagues of what the projections of pH changes might take place, where we were in 1900, where we are right now, what kinds of impacts will we have. Yellow represents very concerned time frames, and red represents situations where we're in very dire situations. We're already in upwelling waters where we're very, very concerned. We would see impacts on a number of different organisms. And we move out with the projections out to pH changes near the end of the century. We would see impacts on a variety of different organisms. That's what we know from the literature this far. So, what we know now understanding is, here's where we're at. Much our president understands are from very simplistic experiments, usually short duration experiments with single species under very short incubation periods, usually 2 weeks or 3 weeks, and extreme pH changes. What we don't know yet is what is the response of population, what the synergistic effects are, what the physiological and evolutionary adaptations are, what kind of species replacements might take place in the field, the community ecosystem response, and the impacts of global climate change. The carbonate cycle is so important in effective amount of CO2 management. What we have done about this thus far is, by working together at the federal and the state level, is develop legislation to address this issue. And in 2009, we developed the Federal Ocean Acidification Research and Monitoring Act, which was signed by the President, that authorizes NOAA and other federal agencies to work on this problem. And the Congress asked us not only just to look at the science, but also at the adaptation strategies, which will provide a whole new source of research areas that, frankly, none of the federal agencies have addressed before, and provide a whole new idea. So understanding adaptation strategies is going to be a tremendous challenge to this research community. We also developed an interagency working group. They're hard on working on a national program for ocean acidification, which has to be reported to Congress in April. And I'm glad to say we're working very hard to produce that national plan. And it's amazing how well these agencies are working together. I'm very proud of this. NOAA, NSF, NASA, USGS, Fish and Wildlife Service, Marine Minerals Management, Navy, Department of State, EPA, all working together on the plan. So we're working to make things happen. Within NOAA, we have a plan. It will be on our website in about 2 or 3 weeks. It has monitoring trends, ecosystem responses, modeling changes, adaptation strategies, education and outreach. We hope to work with our community here, the universities here, and the universities along our coast, to work together in a cooperative effort on this, particularly with monitoring and ecosystem responses. This is where I think we as a community can work together very hard. We're very lucky here to have several federal laboratories, National Fisheries Service, EPA, working closely as colleagues with the University of Washington to carry this work out. So, in conclusion then, I wanted to say that there is, since the beginning of the industrial age, we've already seen the pH change, when the pH 30% increase in acidification. And we may expect to see 0.3, 0.4 pH change by the end of the century if we don't change our habits in use of fossil fuels for energy. Possible responses of the ecosystems, frankly, are speculative at best. It requires much more research on impacts and vulnerabilities. And if we're going to really do this, we need to find an observational network with modeling and research to address this issue. I think I'll stop there. I want to show you 2 slides in the end, but I think it's good to stop here and answer some questions.
Thank you, Dick. I'll leave you to take questions from the floor. We have time for about 5 minutes of questions, and then we will have a reception outside afterwards. But back to you.
Yeah.
So, your map shows that acidification can be worse at the poles than anywhere else in the world. And yet, our recent surveys in the polar regions show us that those systems are almost entirely shellfish dominated. And so, we be seeing since they, if I look at the map right there, already in a corrosive environment. Will we begin to see the effect of ocean acidification at the poles?
Yeah, I think our problem has been is we haven't looked. Right? So there's an interesting study on the oysters that just came out recently that suggested that if you do your experiments in the laboratory and you start the experiment at 280 parts per million, and just look from 280 to 360, you see changes. So we have to consider looking at this properly, and as experimentalists in laboratories and as field experiments, looking for those changes that are taking place. We haven't done that. We need to look at sediment trash samples. We need to look at sediments. We need to understand it. Very good. Yeah.
Hi, Dick. Craig from Bell. I was wondering if you would share your thoughts on the adaptation potential, thinking if is the acidification rate too great for most species to be able to adapt, or is there potential there for adaptation?
What I tried to convey is that our understanding of adaptation is that the most recent situation possibly we don't know. We haven't studied, as a community, we haven't studied adaptation for this particular process at all yet, for ocean acidification. I'm not saying that earlier. But there are some examples, and I want to give you two examples, at least one example that I'm aware of. With respect to the hatchlings, for example, the first adaptation strategy we developed was a very simple one. Turn off the spigot. When the waters are corrosive, turn it off. Well, it don't work for a while until they're almost corrosive all the time, right? But we developed another strategy, and I think this is a particularly important one that was actually developed by Mark Green on the East Coast. Well, why don't you pass the water that's coming into the hatchery through a limestone bed that would allow you to change that pH before it gets into the big containers that they have. And what he did was very smart. He just said pass them through old clamshells. You know, that's not really changing the environment much, but it increased the pH and saved those clams in that case. And they're trying that out at Taylor Shellfish Farms, and that appears to work. They haven't figured out all the bugs yet or optimized it yet, but those are simple things we can do if we are developing those strategies in the laboratory to show us how to do that. That's why I bring this up in this community. You're the guys who can actually do this in the laboratory and show us what the optimal conditions for that. And then as we learn about how the organisms respond, we can all begin to think of more adaptation strategies. I think we need to get started at the experimental level. Yeah.
So going from that sort of local engineering perspective, one thing that tends to be a little bit overwhelming about the CO2 story is that it is a global thing. And we look at solutions, and they tend to be political, institutional solutions. And when we filter down to the individual, driving less, using less energy, just seems to be an overwhelming problem. So given that, and the rapidity with which you've shown us things are happening, give us your thoughts on geoengineering solutions.
Well, I hate to be pessimistic, but I think I have to be honest. Most of the geoengineering approaches to global climate change have not considered ocean acidification at all. They sort of ignore the problem and try and figure out, okay, how can we cool the earth? But they don't worry about CO2. The perception is forget about the CO2, we're just trying to cool the earth. And that's the problem. There are a few exceptions, 2 or 3 suggestions for large-scale geoengineering solutions that would affect ocean acidification. None of them have been proven to even at small scale very well yet. There's iron fertilization, which most knowledge say will not work. Phosphate iron fertilization could enhance ocean acidification in subsurface waters quite a lot. CO2 sequestration from the atmosphere to the deep ocean. Prolong the problem over time if you really screw up the ocean, so that's not such a good idea. There's been suggestions that you use limestone. The cost of using limestone or other approaches can only work at a very regional level, can't work at a global level. So you haven't got really good solutions that really address the situation.
It seems like it's a very complex, broad-scale issue. And what I wanted to know is, with the legislation you mentioned, did they actually increase funding, or is it just the directives, or what's going on at the national level?
To be frank, what's going on at the national level is we're at one level. The 2010 funding level for ocean acidification was at about about $10 or $12 million level nationally, maybe a little bit more than that. What happens in the future is dependent on the new Congress. And I guess it's good to remember that. All the legislation is needed there, but it's in the appropriation process. The new Congress takes over the appropriation.
There's no lobbying organization.
All of the NGOs are working very hard. That's why I do this testimony before Congress, to address these issues with all the agencies that are involved. As you well know, the Congress is making the decisions.
So I think I'm kind of on the same line with what Julia was asking about awareness or from the federal or legislative level. Is there any predictions about where these impacts will be felt, like the oyster hatchery, or it seems like events like that are what make people take notice, especially about legislation take notice. So, are the acidification going to be underwater, tourists not seeing coral reefs, or will it start to be more coastal, or do you have any ideas or thoughts about that?
Well, again, we're limited by what we know. And most, I'm trying to suggest, there's not a lot that we know yet. But we know that the impact on coral reefs could be quite severe. Some of the projections suggest that by the end of the century, calcification could drop as much as 30 to 60%. And some would argue that that would really threaten the whole ecosystem and the whole ecosystem. That alone is very important to humanity because 25% of the fisheries that we need spend some time in their life in the coral reef ecosystem. And so that represents a significant part of our food resources. Humanity depends on food, protein from the sea to feed about 1 billion people. So that's a critical issue from that alone. We know we see things with respect to sea urchins and oysters, and we think that there are going to be some connections with the seafood as well. And so we have to work hard to develop those connections as scientists and make them very strong connections and convey that to our policymakers that these are critical issues for plain science. I think our job right now is to let you guys know how serious an issue this is and hope that you would, in your research, think about the kind of experiments we've done and get that in the picture. That's what our job is. I wanted to end up with 2 slides if I could. And these are just thought slides. But I just wanted you to think. Usually, one of the questions that comes to me is, if we look in the geological past, So this is the PEPM 55 million years ago when there was a significant increase in CO2, full warming and CO2 from methane release and oxidation to CO2. Very rapid, occurred over a 10,000 year period, not 200 years like what we're doing. And we can see dramatic impact on this event. This caused a shoaling of the calcium carbonate condensation depth about 2,000 meters. That 10,000 year event took the oceans about 100,000 years to recover from that because of the slow process of circulation, neutralization of all the carbonates that cause the rise of carbonate condensation. And as you see here, it caused the extinction of 30%, 50% of the working. There is a fairly clear example of what the CO2 event of high magnitude does and how long it takes to recover from that. The second slide I wanted to show you, if you look at all the major extinction events that occurred throughout geological history. So here's the present, here's 500 million years ago. You can see the extinction events that occurred. And associated with the extinction event, the KP event here, we know a little bit about acidification events as well as loss of oxygen and other effects. But these were major extinctions in the calcifying species, sometimes 95% of corals were extinct. They had to re-evolve. They had to start over again, taking anywhere from 2 to 10 million years to re-evolve. So the decisions that we make as human beings about the release of fossil CO2 going to have impacts on our ocean ecosystems that will be witnessed for hundreds of thousands of millions of years. These are serious consequences that we need to be dealing with. Thank you.
Receptions outside. Control, dish outside.
Oh, that's great. I just stacked a couple of them.
I just like
So I didn't have my brother and son. And then, but I was missing like between 0 and 500 basically. So I was working on it.
She's one of those webinars.
All right, guys. What are you doing there? How are you? Cash, you want to sit downstairs for me? I recognize. I'm Mark.
Yeah, which she talked about.
Jeff?
You guys talked about. I think it's in the forest paper, right? That she talked about.
Oh, really?
Yeah, I think
so
it was
you're in UW class?
No, we're doing
Cool. Okay. So what you guys are in for? Two. How many ways you could look
We should be around.